So last time we saw that we can solve the Schrödinger equation for a particle in a box with a wave function that is sine of ax plus b. And we found that for this wave function with a boundary conditions of a particle in a box, we found that our conditions are al is equal to k pi, and b is equal to n pi. And then by putting a back into our eigenvalue for our energy, we got out that this is the energy for different particles in the box. Now you'll notice that k can take on values that are 1, 2, the integer values, and so in a sense this is a quantized system, because the energy depends on integer numbers of what we call the quantum numbers, and so this here is a quantum number. And it only really depends on the size of the box, and once the size of the box is determined, basically you've got some integer multiple of h squared divided by hm, and then that will go up to the power of to the squared power. So that's really interesting. So we can actually see that now we don't have a continuous a number of allowed energy levels, but we only have discrete, and so that makes it a quantum system. So what is now our wave function? So all we need to do is just rearrange this, k pi divided by L, and we just put A in here, and we just put B in. So it's really quite simple. So we find that we've got sine of k pi over L times x plus n pi. And so this is our wave function. However, for this to be correct, what we do have to do is we have to normalize it, because for our matrices we need to make sure that they are Hermitian, but you don't need to worry too much about that. And one of the conditions is that they are normalized. So this integral here has got to be equal to 1. And what this states, what this shows us basically, is that the particle must be somewhere. So the particle must exist between the extent of the box. So it's got to be somewhere. And so if you do this integral, which you're now able to do after our integration and differentiation discussions, you should find that the factor that you multiply this by in order to normalize it, it's called the normalization constant, is 2 over L to the power of square root, which is the same as the square root of 2 over L. And so our final wave function is equal to the square root of 2 over L sine of k pi over L x plus n pi. So you can now start to see how we actually calculate. You basically find a trial. This is called a trial function. Put it into our differential equation, in this case the Schrödinger equation, and we find out, according to some boundary conditions, what the parameters that we've chosen actually are. And then we can normalize it using this integral, and we can come out with our final wave function. So this is what we do, and we can do it for many different systems. Most of the time they come as an approximation because we can't solve it exactly, but in the case of particle in the box, in the next problem, which is a harmonic oscillator, we can solve it exactly. So what I wanted to show you is just a kind of an application of this, or how on earth you'd actually think about this in the real world, a real world problem. So let me just go to the internet. So on one of my recent blog posts has been on looking at the particle in the box, and a very cool experiment where they can actually see the different energy levels and see those different wave functions. So the first thing you need to know is that is that the experiments use what's called an STM, a scanning tunneling microscope, and basically the way this works is that you move a tip over the surface of a sample, and you have a voltage between the two, and electrons tunnel up into the tip, and you measure some sort of current. And so usually how these things work is by changing the voltage, you can excite different electrons out of your sample, and they go into the tip, and you can measure the current, or the number of electrons per second, the coulombs per second, and then that can give you an idea of how close you are to your atoms. And so as you go over your atoms, you're going to you've got a feedback loop that can maintain a constant current, and what you end up doing is building up a whole bunch of traces at different positions. So if we now look at kind of the results, and I might do a little bit more on STMs, scanning tunneling microscopes, because they're very, very cool systems. But for now, let's just look at the results. So for a particle in a box, as we saw earlier, this is kind of what the potential looks like. And we showed that for the wave function, we can solve it like this. This can be our wave function. Now I've set my b to be equal to 0, and that just simplifies things a little bit for us. And so how does the experiment work? So the experiment that we are going to look at is when they put together a whole bunch of palladium atoms. They lined up 20 of them, and so you can kind of think about this as the particle in a box. The electrons are attracted to the nuclei, and they can move freely across the whole length, but it's very unlikely that they're going to go past the extent of these atoms. And so this is kind of like the particle in a box. And what they did is they changed the voltage on the tip of the scanning tunneling microscope, and they were able to excite different energy modes, and they found that these modes approximated the solutions to a particle in a box. So I'll show you the picture now. So these here are the square of the wave function, so they're the wave function squared, which is our density, our electron density, and you can see this is for the zero order mode when k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4. And you can see that there becomes more oscillations in the wave function. Now, if you change the voltage of the tip, you can excite these different modes, and you actually get pretty good approximations here for the particle in the box. You will see that it's slightly favored on the edges as you get to higher order modes, and we can explain that using our harmonic model, which we'll develop in the next video. But yeah, I just wanted to show you that this is kind of an actual example of how a particle in a box can be shown to work, and it gives you a really good quantum intuition as to how a quantum system will work.